So this topic is called equilibrium, which should be bringing about a wee bit of deja vu with you, because this is a topic we did in AS2. Now, it's not a different topic, it's just that we're going a wee bit further with equilibrium. So we kind of stopped at a certain point at AS, and now we're picking it up and going further at A2. Before we do that, the first page kind of goes through a wee recap of everything you should know about equilibrium from AS, because whilst we are learning new stuff in this topic, in exams they still can bring up stuff you did learn at AS, so it's worth recapping, make sure you're happy and understand it. So very quickly, just going to go through this first page and just give you a rundown of the main points that you should know from AS equilibrium. So the first thing you should remember is that equilibrium is always to do with reversible reactions. So if I just sketch out an imaginary reversible reaction, let's say it's 2A going to B, and they're both gases. That's a reversible reaction, and that means if I do this reaction in what we call a closed system, in other words, nothing can escape, we'll set up what's called a dynamic equilibrium. Because if I put some A into a box and let it react, it's going to turn into B, but then B can return back to A. After a wee while, the forward process and reverse process will kind of even out and go at the same pace, and we'll end up with a certain amount of reactants and a certain amount of products. It's called dynamic because the reactions are still happening, but it's called equilibrium because it's remaining constant. That's the basis of dynamic equilibrium. It's got a definition: the amounts of each reactant and product remain constant, and the rate of the forward reaction is equal to the reverse reaction. A little bit of terminology about equilibrium. In terms of the position of it. So depending on the way the reaction works and the conditions, temperature, pressure, etc., I might end up with lots of the reactants in my closed system or lots of the products. The terminology we use to describe that is the direction of the equilibrium. If the equilibrium lies to the left-hand side, it's got lots of the reactants in it. And if it lies to the right-hand side, it's got lots of the products to it, which is described here. So equilibrium lies to the left, there's not much product. Equilibrium lies to the right, there's lots of product. We can change the position of equilibrium, and Le Chatelier's principle gives us a kind of work out what the effect of a change will be. There are kind of four main things you can do to affect an equilibrium. You can change the concentration of a reactant or product, affect the temperature, affect the pressure, or add a catalyst. Just to quickly work through those. So the idea of Le Chatelier's principle is that your system will always try to oppose a change that you do to it. It's not as if the system has a mind of its own, it's just in terms of probabilities and thermodynamics. That's the way it kind of works out. So you can imagine the system trying to oppose everything you're doing to it. So with concentration, if I go back to this example, if I added more A to my equilibrium once it's set up, that's disturbing the equilibrium because I've added more of the reactant. To oppose that change, what the equilibrium will do will be trying to reduce A and turn it into B. So if it tries to decrease concentration of A because I've increased it, it's going to move the equilibrium to the right-hand side in order to use up A and reduce that change that I've introduced. So that's an example of the concentration. Temperature, you'll only be able to understand the temperature change if you know if the reaction is exothermic or endothermic in the forward or reverse direction. So let's say, for argument's sake, this reaction is exothermic forward direction, which means that the reverse reaction must be endothermic. So if I increase the temperature, the system wants to oppose that change. So I'm increasing temperature, the system will want to decrease temperature. It will decrease temperature by favouring the endothermic reaction, which in this imaginary case is the reverse reaction. This will cause the reverse reaction to speed up, which will push the products back into reactants, which moves the equilibrium to the left-hand side. So that's an example of temperature. Pressure is the next one. Pressure, if you remember, is only really important when it comes to talking about gas reactions, as this example here is showing, and involves counting the gas on the left and counting the gas on the right-hand side. So in this reaction, I've got 2 moles of gas in the reactant side and 1 mole of gas on the right-hand side, on the product side. So let's say I increase the pressure. So if I increase the pressure, according to Le Chatelier's principle, the equilibrium wants to oppose that change. It wants to decrease pressure. It can decrease pressure if it moves the equilibrium to the side, which is fewer gas particles. Because the fewer particles you have to squeeze into the box, the less pressure they're going to be experiencing. So in this case, to decrease pressure, it's going to move to the right-hand side because there are fewer moles of gas on the right-hand side of this equilibrium, and that will decrease the pressure. The final condition you can change is adding a catalyst, and the important thing to remember is a catalyst will speed up a reaction but will do nothing to your equilibrium or the position of it. The reason for that is you've got two reactions going on in equilibrium, the forward and reverse reaction. And the catalyst will speed up both of these by equal amounts. So the overall reaction is quicker, like you'll reach your equilibrium quicker, but it's not actually going to change the position of the equilibrium. So everything will stay consistent in terms of your proportions of reactants and products. So that's a recap of Le Chatelier. The second part of the topic was looking at your Kc values or Kc expressions. So the idea is if you've got a reversible reaction like this, which you're putting in equilibrium, you can describe where that equilibrium sat by converting this into a Kc expression. And the general idea is if you've got a reaction like this, you put the products on top. Remember the square brackets refer to concentration, so that's concentration of C, concentration of D. And you put the powers of their balancing numbers or mole numbers at the top. So C to the power small c, D to the power small d. And do the same at the bottom with the reactants. So concentration of A times concentration of B, and then put them to the powers of their balancing numbers. Perhaps it would be easier to see that in like a real life example, so let's just do one quickly. So if we had the Haber process, so N2 plus 3H2 reversibly goes to 2 ammonias. So if I wanted to make that into a Kc expression, I would put the products on the top, so concentration of ammonia. I'm going to square it because that's what the balancing number is for ammonia. On the bottom line, I'm going to put N2 concentration, but just by itself because there's no balancing number, and then H2 cubed. And that would be my Kc expression. You may remember we have to be able to work out the units for a Kc expression. Not too hard to do, just takes a wee bit working out. The key idea is that if we're saying there's concentrations in this Kc expression, concentration is always measured in moles per decimeter cubed in this topic. So what we're basically imagining is we've got molarity or moles per decimeter cubed on the top, so molarity squared over molarity for N2 times by molarity cubed. Simplifying that out, that's m squared over m to the 4, which is going to be overall m to the minus 2 if you just curve cancel that fraction down. Turning it back into like a proper unit, capital M is just standing for moles per decimeter cubed. And I'm going to put it to the minus 2. And if you think about what that does, that minus 2 will apply to both of these things. So the moles will become mole to the minus 2, and the decimeter to the minus 3, multiplying them together, I'm going to get decimeter to the 6. So my units for this Kc expression will be moles to the minus 2, decimeters to the 6. And once we formed those Kc expressions, we didn't actually go very much further with that at AS. We looked a little bit about the values or sort of ballpark figures for the values, if they're high or low, because that can give you an indication of where your equilibrium lies, whether to the left or the right hand side. If you've got a high Kc value, which is much bigger than 1, that would indicate the position of the equilibrium lies to the right hand side. Sort of working that out, if you look at the fraction here, you can go back to this general case. If I've got lots and lots of products, which would make sense if it's on the right hand side, that means that the values in the top would be very large. Just for example, it might be like 1,000. And then the values in the bottom, left hand side, be very low because the equilibrium is very much on the right hand side. So it might be 1, for example. That gives you a very large figure, 1,000 for example. So it's much bigger than 1. So that tells us a high Kc value indicates a right hand side your equilibrium. Turning it round, a low Kc value indicates the position lies to the left hand side. So that means low value means less than 1, because if we imagine the reverse case, if I had lots of the reactants but not very much products, an example figure might be 1 for the top line of the fraction for the products and 1,000 for the bottom line for the reactants. So that's clearly a very bottom heavy fraction, which means a very small number, much less than 1. So the value, whether it's above 1 or below 1, gives you an idea whether your equilibrium is to the right hand side or the left hand side. The one thing just to very touch on quickly is the temperature can affect that Kc value. So temperature, that's actually a wee typo there. Changes in concentration, I should say. Changes in concentration or pressure or adding catalyst don't affect Kc value, but temperature does. I mean, looked at a few questions where you try and work out the effect of that. And that's where we got to with AS. You might have thought a wee bit strange at the time that we did all this kind of fraction work to get these Kc expressions, but we never actually used them. And that's where we're going with A2. Pretty much summing up A2 equilibrium, it's basically trying to put numbers into the Kc expressions and doing some calculations. So that's where we're going, as we'll find out on the next page.